All right, this should be our last lesson on lines, and the last task that we want to do associated with lines and curves through space is to perform integrals on these lines, along these lines. So a motivating question that we might consider to get into this lesson is, how can we calculate the total amount of something if it is distributed along a curve through space? And here's a simple example. You're hiking through a field in the XY plane, and you're picking strawberries. You're picking every strawberry that you see as you walk through this field. Supposing that you follow a path through the field given by this parameterized function right here that has an x and a y part. If that is your path through the field, and the density of strawberries in the field is given by some function sigma, then how many strawberries will you pick in 10 minutes of walking along this path? So that would be an integral from t equals 0 to 10, somehow along this path of this density function sigma. So we're now going to look at two ways of defining this procedure of calculating this. And as the name of the lesson suggests, it will be an integral. So we want to note a couple of things. First of all, the integral of this object is going to be along this path, whatever the path is, and the density function is independent of your particular way of traversing the path. So put another way, this answer should not necessarily depend except for this 10 minutes part, and maybe I should not have used that. Maybe I should have made it 100 meters or something. But apart from this time limit, and let's just go ahead and change that to, say, 100 meters, this is going to be independent of the way that you traverse the curve. Okay, so we're going to be thinking in terms of intrinsic properties of curves that we've been studying in the last few lessons. So in particular, let's think about the intrinsic nature of this curve and chop this curve itself into small pieces, small lengths, each of which has a width delta s. So we have our long curve, and I'll make a little sketch here. So we have our curve through the field, and we say I'm going to chop this into 1 meter slices, and within each slice these are 1 meter slices, and that will be my delta s right here. Then I say, what is the amount of strawberries in each segment? Well, that will be my density function. Here I've called it f. This will be delta s, and it will be the concentration of the strawberries along that width times the width of this segment. Okay, so the amount in each segment will be here the concentration of strawberries along that meter of path times the width of that length of that meter of path, which is 1 meter. So then we just use a Riemann sum to sum these things up. So we have the limit as delta s goes to 0 of the sum of each of these concentrations times the length of the segment. Okay, and so the way that we condense this Riemann sum representation here is using an integral. The delta s becomes a ds. The function evaluated along the curve becomes f, and this sum here becomes an integral symbol here. So we have the 3 parts of our Riemann sum become the 3 parts of an integral, which is abbreviated in the standard way according to Riemann sums. And what this says is basically, as I walk along the path, the intrinsic length of the path, I chop that path into little pieces, and I measure the amount, the amount per meter in each piece of path, and I multiply that by the length of the path segment, and then I integrate all along the curve. Okay, so this is all a line integral is. It is an integral of some quantity, but instead of integrating over the x-axis, as you were used to doing in Calculus 2, we are now integrating over some arbitrary curve through space. Other than that, it's exactly the same idea. Instead of chopping up the x-axis into pieces, we chop the curve into pieces. Instead of evaluating f of x, we evaluate f at a given point in space. And instead of integrating over x, we integrate along the curve. So it's exactly analogous to Calculus 2. And in fact, everything that we will do here will be about turning these three-dimensional geometric integrals into ordinary Calculus 2 integrals of the kind that we're used to seeing. So we could call this the conceptual approach here. We have some curve with an intrinsic property of arc length, and we chop that arc length into little pieces, and we do an integral along it just like we did in calculus. Unfortunately, as we've seen in past lessons, it's not always possible to get the arc length function exactly, given the parameterization. It might be too complicated to get an explicit, simple, closed form solution for the arc length function and to reparameterize the curve in terms of its own arc length. So what can we do if all we have is a parameterization with respect to some additional parameter t? And so that introduces what we might call a practical approach. Okay? Instead of chopping up the curve into individual little pieces, we now chop the parameter into individual pieces. And now each slice of curve may have a different length as the parameter goes more or less rapidly along the curve. But nevertheless, we learned how to estimate the length of each of these segments in a previous lesson. So now the length of each segment is given by this quantity here, r prime of t magnitude times delta t. And we can again approximate the amount in each one of these segments by the length of the segment times the concentration within that segment. So we have these two pieces. We construct then a Riemann sum of these approximations. Here again is the length of the segment, approximately, the concentration within the segment, multiplied together to get approximately the amount within the segment, sum them up, and then take the limit as my slices in my parameter goes to 0. That gives me a different integral. That gives me, here is my r prime of t dt, the length of the segment, the concentration within the segment, and the time interval or parameter interval over which I'm integrating. These are two ways to get the same answer, and so we now introduce a definition. We write this bit here. This is called the line integral, and this is the notation that we use for a line integral. We showed how you can get that notation by thinking of the problem in a conceptual kind of way, using concepts that are intrinsic to the curve itself. And so this is conceptually how we should think of a line integral. It's the integral over the curve along the arc length of the function f. However, oftentimes the curve c, cursive c, is only given to us parametrically, and we may not be able to do the arc length calculations. So to actually calculate that, we use the second approach, and we define ds to be equal to r prime of t magnitude dt. F is the same, and instead of integrating over s, we integrate over t. So this is the notation that we use, and this is the actual integral that we calculate in order to compute this object that is named this. So this will become more clear if we do a couple of examples. But before we do that, I just want to say that if this seems confusing, think for a moment that you have already done one kind of line integral. We have already learned how to do this kind of line integral right here. An integral over a parameter t of the magnitude of r prime of t dt, that was called the arc length. Well, using this new notation that we've now introduced, we could write that much more simply as the integral along the curve of 1 times ds, because this object right here is called the length element ds. And so these objects are the same. And it's not quite accurate. Again, these are not fractions. These are simplifications of things inside a Riemann sum. But if we think that ds dt is the magnitude of r prime of t, then it doesn't seem unreasonable that when we're doing integrals that the magnitude of r prime of t dt, and I'll put a approximately here, or I'll put this in quotes, if we're doing integrals, we get this notation here. So This thing is called the length element. So we've already done line integrals. We've done the line integral of 1, and that was called the arc length. It's just how much length is there as I walk along the curve. Arc length. Line integrals are just a natural generalization of the arc length integral to calculate more interesting things. So let's do some examples. So here's our first example. Compute the line integral, which again, this is just general notation for the line integral, where we now define two things in order to compute line integrals. We have to define the curve along which we integrate, and we have to define the function which we're integrating. This will almost always be the case that the function is defined everywhere in space. So this is a 2D problem. The function is defined everywhere within the xy plane. However, the curve is only some subset of that plane, the unit circle. So we have to go along the curve of this function right here. And so this will always be done in 3 steps corresponding to the 3 parts of the notation here. We have to figure out what this part means, what this part means, and what this part means, and we put them all together. And so we'll start with this one. The parameterization of the curve itself. What is the curve? Well, it's the unit circle, and we know parametrically we can write a unit circle as cosine ti plus sine tj, where t goes from 0 to 2 pi. So this step is called parameterization. Maybe sometimes the curve will just be given to you in parametric form. Other times you might be asked to actually come up with the parameterization, and we've had a little bit of practice with that. So first step, define the curve itself. And now we've done that. Second step, I guess it doesn't really matter what order you do these in, but I've done them in this order, is to compute the length element ds. To do that, we're going to need r prime of t, which is negative sine ti plus cosine tj. And the ds will require the magnitude of r prime of t, which is the square root of sine squared plus cosine squared, times dt, and that's just going to be 1 times dt. So for this very simple problem, conveniently, we just get ds equals dt. Typically, life is not so kind. We compute the length element, however. Finally, we take this integrand, and this is the part that people struggle with the most, so here's where you should pay the most attention. We have to take this integrand right here and express it on the curve in terms of the parameter. Okay, so f is a function of x and y. It's x squared times y squared. But on the curve, x equals cosine t and y equals sine t. And so we replace, this should be squared, squared, squared. So on the curve, f, which is a function of x and y, each of which is a function of t, is x of t times y of t squared, which is cosine squared of t times sine squared of t. So we take a function which doesn't depend on t at all, it's a function just of space, but on a curve which has some parameterization, we turn that function into a function of the parameter as well. And now we just need to put these 3 things together. We found the curve itself, which gives us our bounds right here. Here are our bounds. On the curve itself, then we have our ds, dt, and our function f equals x times y becomes cosine squared times sine squared. And now we just, this has become a calculus 2 problem. We have to do it. We need to get these cosine squareds and sine squareds down to something we can integrate. You could take a variety of ways to do that. But I see, anytime I see cosine times sine, I think 1/2 sine of 2t. So I have 1/4 sine squared of 2t. And even that I can't integrate yet. I have to use a half angle formula to get that sine squared down into a 1/2 1 minus cosine of twice the argument. So cosine squared sine squared becomes 1/8 1 minus cosine of 4t. The integral, that's not right, the integral of this object from 0 to 2 pi is going to be 2 pi over 8 for the first part. Negative cosine will integrate to negative sine, and sine of 0 is 0, and sine of 8 pi is 0, so there'll be no contribution from this part of the integral right here. So this just becomes pi over 4. Let's do one more example. Same steps, just different curve, different functions. So again, line integral problem. C, the curve, is now a different curve. It's the parabola y equals x squared. From x goes from 0 to 1. So here is our xy plane, and it is this. So we now have to integrate along this curve, this function, f of x and y, is y over x. So same three steps. We have to parameterize the curve. Since we have this very simple Cartesian form, I'm going to go ahead and let t equal x, and then y equals x squared, which is t squared, so ti plus t squared j. X goes from 0 to 1 becomes t goes from 0 to 1. So here is my parameterization, my step 1. I've done this part. Now I have to compute the length element. To do that, I'll need r prime of t, that's I plus 2tj, and so ds will be the magnitude of r prime, which is the square root of 1 plus 4t squared, times dt. So I've computed my ds. Here is this part of the line integral. And finally, I need to express the integrand on the curve in terms of the parameter t. And so on the curve t equals x equals t, y equals t squared, and so y over x is just t. So there's my last piece of my line integral. I put it together, and I get the integral along the curve becomes the integral from 0 to 1 of my integrand. My integrand becomes t, and my ds becomes the square root of 1 plus 4t squared to the 1/2 times dt. Now this has become a Calculus 2 problem. Basically, as far as I'm concerned, you're done at this point. I expect you to remember how to do a lot of Calculus 2, but we'll just remind ourselves how to do this problem. This is a very simple substitution problem. We don't like square roots of things. However, very conveniently, because the problem was set up that way, the derivative of the inside is basically sitting here on the outside. And so we can do a substitution with u equals 1 plus 4t squared. Du would then be 8t dt. We don't have 8t dt, we have 1t dt. So this becomes 1/8 integral u to the 1/2 times du. Of course, we have to be very careful to change our limits of integration. So when t is 0, u is 1. When t is 1, u is 5. So we now perform the integral using the power rule and evaluate from the two endpoints to get the solution. So we'll do more examples in class, but these are basically all the same series of steps. We have to identify the curve, compute the length element, and then express the integrand in terms of the parameter in order to reduce it to a Calculus 2 problem that we can then solve by the methods of Calculus 2.